Assalamualaikum viewers, hope you all are fine and welcome to you all at my official YouTube channel Chemistry Coaching by Hira. Today viewers, we will discuss a most important topic that is related to valence bond theory in coordination compound. Valence bond theory is the most important theory that tries to explain bonding in coordination compound. Before valence bond theory, there were two scientists, Werner and Sedgwick, who tries to explain bonding in coordination compound. Werner made first attempt to explain bonding in coordination compound. He was awarded Nobel Prize in 1913 for this. After that, Sedgwick, who extended the theory by suggesting that metal ions accept electron pair from ligand in order to achieve the next noble gas configuration. According to Vibity, the bonding between metal ion and ligand is thought to be purely covalent. The covalent bond in metal complexes is formed by the overlap of a filled ligand orbital containing lone pair of electron with a vacant hybrid orbital of the metal atom or ion. In the next slide, we will discuss the postulates of Vibity. There are a number of empty hybrid orbital with a central metal atom or ion in the complex for the formation of coordinate bond with the suitable ligand. The number of empty orbital provided by the central atom is equal to the coordination number of the central metal atom in the complex. If it is 6, then it means 6 hybrid orbitals are oriented in space. If it is 4, then it means 4 hybrid orbitals are oriented in space. The atomic orbitals such as sp.d of central metal atom hybridized to give a new set of molecular orbitals have equal energy and shape. These hybrid orbitals are directed in space and give the definite geometry of the complex. The hybridization that are involved in the geometry of complexes is dsp2 hybridization, dsp3 hybridization, d2sp3 hybridization, sp3 hybridization. These hybridization involve the use of d orbital. If the d orbital is penultimate, it's mean n-1 d orbital. Then the complexes formed after such type of hybridization would be inner orbital complex. If the d orbital involved in hybridization is nd orbital, then the complex formed after such type of hybridization would be outer orbital complex. We will discuss what are inner orbital and outer orbital complex in the next slides. Each ligand has at least one lone pair containing orbital to overlap with the empty orbital of the central metal atom. The number of hybrid empty orbital depend upon the coordination number. Overlapping of orbital forms sigma bond. There is also possibility of pi bond when the overlapping is sidewise. Valence bond theory classify ligand into two categories. The complexes having coordination number 4 have two possible geometries. The geometry would be tetrahedral and square planar. If the complex have coordination number 6, then the geometry will be octahedral. If the complex have at least one unpaired electron in the d orbital, then it will be paramagnetic. Otherwise, in case of paired electron in the d orbital, it will be diamagnetic. You can see in this slide some of the hybridization with their geometries. Sp has linear, sp2 has trigonal planar, sp3 has tetrahedral, and trigonal bipyramidal has dsp3 hybridization, octahedral has d2sp3 hybridization, and square planar geometry has dsp2 hybridization. Classification of ligand in Vibity. There are two types of ligand explained by Vibity: strong field ligand and weak field ligand. These ligand forces the electron of the central metal atom to pair up to provide empty electrons to the ligand for bonding. It's mean that when these ligand approach the central metal atom, they will create such a field that enforce the d orbitals electron to pair up. Weak field ligand are those ligand that are not capable of making the electron to pair up in the central metal atom for coordination to ligands. Upon what criteria we can classify strong field ligand and weak field ligand? Strong field ligand are those ligand that have less electronegativity. Greater will be less electronegativity, greater will be tendency to donate the electron, and stronger would be the ligand. Examples are cyanide, carbon monoxide, and so on. Weak field ligand are those that have greater electronegativity. Lesser will be the tendency to donate the electron, weaker would be the ligand. All halogens, nitro, hydroxide ion, oxalate ion, ammonia are weak field ligands. In this slide, we will discuss the difference between inner orbital complex and outer orbital complex. Inner orbital complex are low spin complex. These complexes are given by strong ligand. The d2sp3 hybridization is used in the structure of these complexes. This hybridization involves the use of two n-1d orbital, ns orbital, and np orbitals. have zero or low magnetic moment, number of unpaired electron is less than free metal atom. Uh, these, these complexes are more stable, inert or non-labile. In case of octahedral geometry, the central metal atom or ion undergoes D2sp3 hybridization. So non-labile complexes are those that do not permit the exchange of ligand from coordination sphere. Example of strong field ligands are carbon monoxide, ammonia and cyanide. Outer orbital complex, these complexes are also called high spin complexes. These complexes are given by weak ligands. There is sp3d2 hybridization involved in the formation of these complexes. This hybridization involves the use of nd orbital, may have high magnetic moment, number of unpaired electron is greater than the metal atom. These are high spin complexes. These are less stable or labile. High spin complexes usually labile because they can replace more than two coordinated ligands with another ligand in the coordination sphere. In this example, you can see that cobalt is in +3 oxidation state and cobalt has 4 unpaired electron. When fluoride ion approaches cobalt, fluoride is the halogen and has high electronegativity, so it is a weak field ligand. It will not create such a force that will pair up the electron in the d orbital. So these will remain as it is and outer 2d orbital will take part in hybridization. So hybridization would be sp3d2 and geometry will be octahedral. Magnetic moment. Magnetic moment, also known as magnetic dipole moment, that is the measure of the object tendency to align with the magnetic field. Magnetic moment is defined as the magnetic strength and orientation of a magnet or other object that produce a magnetic field. It is a vector quantity. Vibity theory well explains the magnetic property of the coordination compound such as paramagnetism. Formula to calculate the magnetic moment of the compound. It is represented by mu and it is equal to under root n into n plus 2, where n is the number of unpaired electron. When n is 1, you can memorize the magnetic moment 1.73. When n is 2, magnetic moment would be 2.83. When n is 3, magnetic moment would be 3.37. When n is 4, magnetic moment would be 4.90 and so on. Applications of VBT. Here we will illustrate the following example of coordination compound. Ions having coordination number 6. In this complex point, some of the ion will be inner orbital complex and some of the ion will be outer orbital complex. Inner orbital complex, you can see that hexamine chromium and hexaamine cobalt in which are in +3 oxidation states. And outer orbital complex are hexafluoridocobaltate ion and hexaaqua iron. Inner orbital complex. First example is the hexaamine chromium. Chromium in this +3 oxidation state, the inner 2d, 2 3d orbital, 1 4s and 3 4p orbitals are hybridized to form this complex. Pairing does not take place because ammonia is a strong field ligand. Weak field ligand. That is why it is an inner orbital complex. The hybridization is D2sp3 and you can see in this slide the electronic configuration of this complex. Geometry is octahedral. You can see all the angles are of 90° and 4 are in the one plane and 2 are in the axial plane. Next is the hexaamine cobalt. In this complex, cobalt is in +3 oxidation state with electronic configuration of 3d6. 4 of the 3d orbital are singly filled and 3d orbital has a pair of electron. Octahedral complex are formed by involving D2sp3 hybridization. It is inner orbital complex. 4 unpaired 3d electron pair up its electron and 2d orbital becomes vacant to accommodate lone, because lone pair provided by ammonia is a strong field ligand and this will create such a force that will pair up the electron in the d orbital to generate vacant hybrid d orbitals that can accommodate lone pair. Electronic configuration and geometry of the complex. 2 vacant 3d orbital rather than outer 4d orbital undergo D2sp3 hybridization, hence it is an inner orbital complex. The complex is also diamagnetic because it has no unpaired electron in the d orbital. Next is the hexacyanoferrate. in hexacyanoferrate. In this complex, iron is in +3 oxidation state. Iron has 5 unpaired electron in the d orbital. Cyanide, being strong field ligand, causes the pairing of electron in the d orbital. There are 2 paired electron in the d orbital. After pairing of electron, there is only 1 unpaired electron and 2 orbital are empty to accommodate lone pair of bonding. The inner 2d orbital and outer s and p orbital then hybridize to d to sp3 orbitals. Geometry of this complex would be octahedral, and you can see that iron and cyanide bond is thought to be purely covalent, and all the cyanide are directed in space along the along the 6 corners of a octahedron. Electronic configuration of iron is such a way that iron is in +2 oxidation state and have a 5 unpaired electron, while approaching cyanide, which is the strong field ligand, will create a strong field, and this field will pair up the electron. Only one electron left behind that is not paired by any one electron, so it is a paramagnetic in nature. In this slide we will discuss the outer orbital complex. I have already told you in the previous slides what are outer orbital complexes. So this one is the hexafluoridocobaltate ion. Huggins suggested that metal can also use the outer orbital for hybridization. As fluorine is a weak field ligand, it does not cause the pairing of electron in the 3d orbital. The central metal, instead of using the inner orbital, use outer 4s, 4p and 4d orbital. The hybridization is sp3d2. It is octahedral complex. You can see in this slide electronic configuration of this complex. Geometry is also octahedral, and this complex is paramagnetic because it had unpaired electron in the d orbital after hybridization. Hexa-aqua iron. It has a similar case that I have already explained in the previous slide, so we can move to the next slide. Complexes of the coordination number 4. There are 2 ways in which complexes can be formed. If the complexes has sp3, then it is tetrahedral complex. If the complexes has dsp2 hybridization, then it is a square planar. Square planar has 4 bonds that lie in one plane, and all the angles are of 90. In this case, the first example is the tetracyanonickelate. In this complex, nickel is in +2 oxidation state and its electronic configuration is a 3d8. The complex is diamagnetic. It has no unpaired electron in the d orbital. We can see in the next slide. dsp2 hybridization is volt. Cyanide, being a strong field ligand, it pair up the electron in the 3d orbital, hence it is a diamagnetic. The empty orbital of the metal atom form a bond with the orbital of the cyanide. The bond is metal ligand coordinate bond. You can see the electronic configuration of the nickel. Nickel has 2 unpaired electrons when it is neutral. When nickel has +2 oxidation state, it has lost 4 of the 4s electron, 2 4s electron, and have 2 unpaired electron. When cyanide approaches the nickel, it will create a force that will pair up the electron in the d orbital. Only one d orbital is empty, and this will hybridize with 1s and 2p orbital, and hybridization would be dsp2 hybridization. The geometry of the complex is square planar. It is diamagnetic because no unpaired electron in the d orbital. Next is the tetrachloridonickelate. In this case, the approaching ligand is chloride ion, and chloride ion has high electronegativity, so it is a weak field ligand. It will not create a field that will pair up the electron in the d orbital. Nickel is in +2 oxidation state. It has 2 unpaired electrons in the central metal ion. The approaching ligand is chloride. It is a weak field ligand, and the outer 4s and 4p orbital then hybridize to give sp3 hybridization. D orbital does not take part in hybridization in this case. The geometry would be tetrahedral. Electronic configuration you can see in this slide, or orbitals of nickel have such type of hybridization. sp3 hybridization of nickel in +2 oxidation state, and complex have such type of geometry, tetrahedral. In this slide we will discuss the limitation of valence bond theory. Valence bond theory suffers from many limitations. It does not explain color complexes. It does not explain electronic spectra of compound. Color complexes like DD transition was not explained by Vibity. It also not explained that water and halide ions form high spin complex and cyanide form low spin complex. does not give the reason. It does not explain that why in some cases the inner and in some cases the outer orbital are used in the hybridization. It does not explain relative stability of the complexes. Certain complexes are labile in which the displacement of the ligand with another ligand takes place very rapidly, while some are inert in which the displacement of the ligand is very much slow. It is unable to predict the relative stability of the ligands. Hope so guys, you will learn from this lecture, and please subscribe my channel and don't forget to press the bell icon. Thank you.